the last time we looked at an airplane with a wing, the lift is acting at the aerodynamic center. It has a negative pitching moment because we made it out of a cambered airfoil. So we put the CG back here so that the pitching moment of the lift balanced out the downward, the nose down pitching moment from the pure coupling from the wing. And so we could pitch trim if we chose this distance correctly. And get 0 for the total pitching moment. The downside was that if we experienced a gust, we get an increase in lift, so we get a vertical gust, and then that messes up the pitch trim because the lift increases, and the airplane wants to pitch nose up, which increases the angle of attack, which increases the lift, which makes it pitch up more. So we call that unstable. And it's indicated by the change in pitching moment with respect to angle of attack. So we talked about how we had a delta alpha, a change in alpha due to a gust, and that the pitching moment became positive rather than 0. So if we take the limit, then we talk about the derivative with respect to alpha. And for this airplane, that's bigger than 0 because a positive increase in angle of attack generated a positive moment, so that derivative is 0, or is greater than 0. Sometimes this is written as, in terms of its coefficient. So we say the derivative of the coefficient with respect to alpha, because we can divide the pitching moment by QRSB, and it's still going to be greater than 0. And often this is written with a subscript instead of writing the whole derivative. So we define this notation here. This says Cm derivative with respect to alpha. And so if you see this derivative greater than 0, it means it's unstable. And often you'll plot pitching moment versus angle of attack to look at that slope. Either Cm or M. So if you plotted the pitching moment coefficient versus angle of attack, you'd see a plot that looks like this, where this is a positive slope. So if you took this airplane in a wind tunnel and tested the airplane and collected points of the pitching moment of the airplane at different angles of attack, plot it, you'd see that positive slope. And you'd say, okay, my airplane's unstable. So pitch trim, definitions here, pitch trim is where the total moment is 0. So that's our equilibrium that we have to have when we talk about stability. So we're flying along, pitch trim 0, straight level, everything's cool. We get a gust, and then we look at pitch stability. Which is the sign of how the pitching moment changes with angle of attack. Positive, it's unstable. Negative, it's stable. So let me show you an example of how we can fix this airplane up. Does everybody see what's missing? What's on a normal airplane? The tail in the back And so I'll show you why that helps. We need to redraw this picture. So with a horizontal tail, our airplane looks like this. Here's our wing. Here's our horizontal tail. Here's the lift wing. Here's the lift, the horizontal tail. And to make this easier, I guess, think about, let's use a symmetrical airfoil this time. So that this pitching moment from the airfoil is zero. Remember, a symmetrical airfoil has zero pitching moment. And let's put the CG right here. And so this is easy to trim because the moment arm is zero. And so all we have to do is adjust the horizontal tail times its moment arm to zero lift, and we're trimmed. Everybody see that? So we have lift equals weight here. I put the CG right there because, as I said, it makes it easier. Symmetrical airfoil, we're good. Set this lift to zero, and we're trimmed. So far, so good. So we have pitch trim. So now about stability. We have delta alpha test. So we get a delta lift of the wing and a delta lift of the horizontal tail. So both of these increase. Which way does the airplane pitch? You get no pitching out of the wing change, right? But the tail, because it's behind, is now going to cause a nose down pitch. So delta alpha gust, we get these lifts, horizontal tail is behind the CG. And so we get a negative pitching moment. Delta M with response to the gust. So change in pitching moment with change in alpha is negative, and we write that as CM alpha lethal limit. With the coefficient, we'd say CM alpha is negative, and this is pitch stable. Because a moment is generated by the disturbance. Remember definition, we have equilibrium, have a disturbance, we get a moment generated by the disturbance to reduce that disturbance. It's going to pitch the nose down, it's going to decrease the angle of attack. So this all works. Now what if we start moving the CG? And say, well, we don't really want the CG right there. Or right here. Let's put some heavy stuff back in the back of the airplane. And we'll move the CG back to here. Well, we can adjust the lift of the tail, because now we're going to get a nose up from the wing and a nose down from the tail, so we'll have to crank up the lift of the tail to balance that, so we can still get pitch trim. What about stability? We don't really know, because we're going to get this delta lift here and a delta lift here. And it's going to depend upon the distance here versus the distance here, right? Because now we're going to get a nose up from this part and a nose down from this part, so it depends on how far we are back as to what's going to happen. And in fact, you can get, so let's say at this CG position, now we've got CM alpha 0. It's not stable, it's not unstable. But then if we move the CG even further back, then we're going to get more nose up from the wing than from the tail, and we'll be unstable. So there's a critical point at which the CG can be at where we start to lose stability of the airplane. And in fact, that's called the neutral point of the airplane. And all I want you to remember out of this whole thing here is that in a conventional configuration, if you move the CG back too far, you can go from a pitch stable airplane to a pitch unstable airplane. And it's really important when they load airplanes, when they get ready to fly, is that they'll calculate where the CG is, compare it to this neutral point, and figure out whether it's safe to fly or not. And small airplanes like the 182, you're limited to where the passengers sit and how much baggage you put behind the passengers for that reason. So how does this pertain to your glider? Well, you're putting your wing and your tail on your airplane, and you're sizing them. So you're choosing these locations, and then you calculate the CG based on that formula that I gave you. So if you calculate your CG, and you design your glider with the wings and all that, and it turns out when you try to fly it, it wants to pitch up and pitch down and flip, your CG is too far back. Now you can't just go into X-plane and just plug in a number that's further forward, because I'm requiring you to use that formula that includes the weight of the wing, the weight of the tail, and everything else. So if your CG is too far aft, what's one thing you could do to shift it more forward? Like your airplane's wanting to flip. What do you have control of? The what? Person. Yeah, so you can move your pilot to a different spot, right? That's going to be kind of weird if you have your pilot sitting up here on the nose of the airplane. Right? But you can adjust that. And also shifting the location of your wing and your tail helps out. So you can move your person, but if you have to move it too much, what it means is maybe you just need to move your tail further back, because that increases this moment arm and you can stabilize it that way, or you can make your tail bigger. Because the bigger the tail is relative to the wing, the more effect it has, and so it will help balance out that pitch from the wing. So that's why I wanted to go through this stuff now, is because you're hopefully flying your gliders pretty soon, or if you haven't already. If you put the CG in and it wants to flip, then start moving the pilot forward and making the tail bigger until you fix it. Let's see, we talked about the marble and the bowl, right? And notice that the key to trimming this airplane is the ability to shift the lift on the tail up or down, right? We said, well, we're going to have to increase or decrease the lift of the horizontal tail to match the pitching moment of the wing. That's why typically you will have some kind of device on the tail where you can change the lift of the tail. Either you move the tail completely up and down, so you can tilt it down, you get lift up, or you can tilt it up and get lift down to balance. Or we put an elevator on the back where we can change the camber and get less or more lift there to balance it. questions about what will be going on Wednesday or Friday? So on Wednesday, yeah.
For the top there, we have a few slots created. How do we have the top there?
How do you locate content?
Like we need to know something specific. Or we have to apply it.
Well, you want, I mean, your pilot viewpoint is going to be a certain slot in the piece. Okay. So then you'll have to show up the diameter of your fuselage at that point. Where the pilot sits is big enough to have it on. Yeah, but I guess you'll do this if you have the pilot standing in the airplane. You saw that from 6 foot down, right? And sitting down, or however, it's not really good. How does the pilot fit in that location? So on Wednesday, we'll be meeting here. So we'll run the PowerPoint presentation if you want to do that. PC over here. So have the PowerPoint available for the team captains, right? Either on a USB stick or be able to access it from your email. It should just be a deal like that. So your group will come up and present up here. If you want to draw on the whiteboard, you can do that. And then your reports are due. Hard copy reports. These don't get uploaded to Blackboard. Hard copy reports are due on Wednesday. Yeah.
Okay. Is that
I'm sorry, what did you say?
Wednesday?
Wednesday, yeah. During the presentation time, that's when I'll collect the hard copy of the reports, and then on Friday we can walk.
Is that Friday morning?
Huh?
Friday we fly to the
Yes.
Okay.
Just like this assignment says.
Okay. So the ingredient full page or is just limited to a full page?
Limited to a full page. If you write one sentence, you won't get one day. Yeah. Tell what you did.
Yeah.
Which I'll go crazy. I will have, Friday will be in back in Walsall. I'll have the joystick like these in the room set up so that you can sit in front of the monitor. I'll turn the monitor around so you can look at it. It'll also be projected up on the screen on the top. You'll be sitting up there. If you have a joystick at your house that you've been using and practicing with, you're welcome to bring that. We'll plug it in. Hopefully it will work. Usually I don't have a problem with that. So that's what's available for you to fly with. Now we only have 3 groups this time, so we'll probably most likely have time for everybody to fly twice. So if you get up there and something just goes disastrously wrong, you get a chance. But again, make sure your pilot is practicing. I want to talk about, there's no more questions, talk about maneuvering flight. We've been talking about straight level flight and climbing flight where lift is pretty much equal to the weight, although when we're climbing, the lift is a little bit less than the weight. When you do maneuvers, that's when you pull cheese. You can see your lift maybe 2 or 3 times the weight of the aircraft. Because the lift has to provide part of that force to cause you to follow a circular path. Just like when you have a ball on the end of the string pulls on the ball and keeps it from going straight, it causes it to follow the curved path. So we'll do a steady state turn first. So we're doing a level turn where our flight path angle is 0. It means we're not climbing or diving while we're doing the turn. So a top view of what's going on looks like this. Here's the center of the turn. Here's the airplane up here. And it's following a curved path of radius r about the center of curvature. And this is an obvious maneuver that you need to be able to do because you need to be able to go from one heading to another heading. We talk about turn rate as heading angle rate. So if you're changing your heading angle, psi, and psi dot is the turn rate. And if we look at the airplane going through an angle psi, like that, and then the arc length here is S, by definition of an angle in radians, the arc length is equal to the subtangent angle times the radius. And if we take the derivative of this, the change in position is equal to the angular rate times the radius. And we know that change in position with respect to time, that's just velocity. So the velocity, the forward velocity as it goes through that arc is related to the turn rate by the radius. All right, so now I want to look at a back view of the airplane. So here's the center of the turn right there. Here's the airplane. And we need some kind of force to make it do that turn, to make it do the circular path. And the easiest way to get that is to bank the airplane so that part of the lift vector provides that centrally acting force. And this is the bank angle. Phi is the angle of the wings to the level flight. So that gives us the centrally acting force that causes the circular motion of radius r. And this is a back. And I emphasize that because the bank angle is positive right wing down, just by definition. All right, so on this diagram, this is L sine phi. This is L cosine phi. So those are the two components. So now I'm drawing a free body diagram. Let me make it bigger over here because I got kind of small there. But that's the picture that we're looking at. So now I'm going to zoom in on just the airplane. We have to remember it's following the circular path, and so we need a centrally acting force. So let's draw a big picture of the airplane here. Still an aft view. This is the bank angle phi. Positive right wing down. And so lift, this is the free body diagram, so there's our lift. We draw the weight downward. Here's those two components. L sine phi, L cosine phi. And so we'll do some of the forces in the vertical and some of the forces in the horizontal. Vertical, we got lift, cosine phi minus the weight. And this is steady state, so it's not climbing or diving, it's just level. So that has to be 0. And then the sum of the forces horizontal, we got L sine phi. And that has to balance the centripetal force needed to do the circular path with the centripetal acceleration. So this provides the center acting force, and this just keeps the weight up. So everybody up to speed on the free body diagram. Here's the lift. It's perpendicular to the infinity. Wings are providing it. That's what causes our turning flight. And then if we look at this equation here, so the vertical, we have L cosine phi equals the weight. We divide both sides by the weight. And write it like that, cosine over here. This is how much lift we have compared to the weight. And this is what we call the load factor. By definition, it's the lift divided by the weight. So if we're doing a 2G turn, the lift is twice the weight. Yeah.
Load function.
It's what?
Load flow. Or load something with that.
Factor.
Factor.
I guess it's called a factor because lift equals N times weight. So it's the factor you multiply weight by to get the lift. So let's say we're doing 2 G's, and why do we call it G's? Is because of the lift compared to gravity. So it's how much extra you are compared to this normal gravity, which is mass times gravity. So do this calculation. If we're doing 2 G's, what's our bank angle? What if we're doing 3 G's? What's our bank angle? You guys have calculators or a phone that can do that? Punch some of those out. What do you get for 2's? 60 degrees. Wow, that's a pretty big bank angle, isn't it? Just to pull 2 G's. It's true, you got the right number. But you're banked way over. How about 3 G's?
70.
70?
70.5.
And let's do 4. Somebody got that? So obviously it keeps going up. ever been in a commercial aircraft flying commercial and you banked 60 degrees? No. I mean, basically, if you're, if they're doing some maneuvers where they didn't get lined up with the runway or they're having to do a go around, 45 degrees feels pretty steep. So you don't see much even close to 2 Gs when you're flying commercial. Now, if you're doing aerobatics, there's a, they do really sharp turns. The other equation that we have here tells us information about the turn radius and the velocity. So let's see, from the horizontal force equation, we solve for R. So R is equal to mv squared over L sine of phi. And I'm going to manipulate this a little bit. I'm going to write the sine of phi as 1 minus the cosine phi, because cosine phi will be in terms of load factor. And for the lift, I'm going to put in mass, I'm going to put in N times W. So that's from that equation over there. The weight is mass, gravity. Oh, this is cosine squared. Oh. Right, sine squared is 1 plus cosine, or cosine squared plus sine squared equals 1. And so then we can substitute in 1 over n squared, because cosine is 1 over n squared. The masses cancel out. And we can put the n inside the square root, so we get an n squared and an n squared. Like that, right? So I'm just doing algebra here. And I'm getting it in terms of load factor because typically you can sense load factor easier than bank angle when you're on the airplane. So here's the horizontal force equation. We just solved for R. Got the sine of phi in terms of cosine, so we put in load factor. And then plugged in lift equals N times W. And this formula says the faster we fly, for a given load factor, let's say 2 Gs, the faster we fly, the wider the turn gets. Which is true even in a car, right? You're trying to do a turn, if you're going really fast, you can't do a sharp turn because your tires have to provide this centrally acting force, and they'll eventually break free of the pavement. Same deal with an airplane, with a given G load factor, the faster you go, the wider the turn gets. So in order to get a tight turn at a given speed, we need as much load factor as we can get out of the airplane. Makes sense as well, right? The load factor gives us the centrally acting force, so the more force toward the center, the tighter the turn. The faster we're going, the wider the turn. So for a tight turn, meaning R low, you want to turn fast to new heading. For a tight turn, we need the maximum load factor we can get. And since load factor is lift over weight, and our weight is fixed, we're going to want the maximum lift we can get. So if we fly at stall or just barely below stall, that's going to give us the most load factor. How are we doing on time? 12? Okay. So this is going to become important because we're going to then look at what the maximum lift we can get out of our airplane is, and that's going to determine how tight of a turn we can do. And this is also true in what's called a pull-up. This is where you're diving down toward the ground. You need to change the pitch direction of your airplane. And so you have to pull G's that way. And in fact, the analysis of that is easier than this. So the free body diagram is going to be really simple. But we're going to find out that for a pull-up, we're going to need Nmax and Lmax as well. And then we're going to talk about that next time. Well, I guess it'll be when we're online. So here's a pull-up. It's a circular path, but now it's in the vertical plane rather than doing a turn horizontally. Here's the center of the curvature. The critical case is when the airplane's at the bottom, because then the lift is up and the weight is down. A not very critical case is when you're over here, because the lift is providing all of the central force, and your weight is not, it only balanced on the drag. So the lift is not having to counteract the weight. So the worst case scenario is when you're at the bottom of the loop, and you need a lot of lift to counteract the weight plus provide the centrally acting force. And like I said, this free body diagram is easy because we only have to look at the vertical direction. Lift minus weight has to provide the centrally acting force to give you the turn of radius r. You can still do this in terms of load factor, because if we divide the weight out of this thing, and then that's load factor easily, and the weight is mass times gravity, so we get gravity times load factor equals v squared over r. So put an n for here, put in mg for this, and here we get r is equal to v infinity over v n minus 1. So we see that we get the same behavior. To get the tightest turn, the tightest pull-up, that is pull up the sharpest, we need the maximum load factor and the maximum lift. And again, the faster we're going, the harder it is to do a tight pull-up. So if you're screaming down toward the ground at a very high speed to turn and avoid the ground, you're going to need more G's. So again, same deal for a tight pull-up. We want maximum load factor and maximum lift. And there's something called a pushover. That's the opposite of this. It's if you're flying up and you want to come going back down. And you'll want the maximum negative G's at that point. And you can look this one up in the book. But we want to focus on these two because they say, okay, maximum load factor, maximum lift. What does that mean as far as what we can do? I want to start there next time, which will be when we do our first online lecture after that.